Hey guys, welcome to my stream. So, I streamed just a couple nights ago and we made some nice progress. We got to a point where I was able to figure out how to implement button input for the joystick and started working on analog and didn't quite get that working. So tonight I'm going to keep working on that. Hey ABDCW says he just opened Twitch and I'm live. Yeah, just started, so welcome to the stream. So honestly I'm feeling a bit tired, so I don't know how long I'm going to last tonight, but well, let's see how it goes. So one thing I did do yesterday is I looked a little bit more online for some documentation on how input and joysticks work, and I fell upon this really cool site for a collection of tools called VIDE or VIDE. And one of the things that it has is it's basically a bunch of tools for implementing stuff for the Vectrex. It has a part of it is an emulator. I suspect it to be quite a good emulator from everything I've been reading here. Possibly one of the best emulators, or the best emulator for Vectrex. He also provides a whole bunch of cool tools for like making games and stuff for the Vectrex. And what's really great is that he documented a lot of stuff. So you can see here lots of documentation, and the section that was interesting to me is down here, Vectrex internals. So here he goes in and he documents the VIDE chip. Hey Alvaro. So Alvaro, I know you were having some cutouts on the stream last time. I tried reducing the quality to 720p, but my tests showed that it was really difficult to read the code at 720. So what I did do though is I had enabled this experimental feature in Twitch to reduce the latency between the time I stream and the time you guys see it, so that I would have a, as they say, like a better experience for chatting and stuff. However, it does also say that doing this means that there's less buffering and could lead to people getting the buffering of the signal of the stream, more often. So I turned that off because I don't have like people constantly messaging me, and I don't need to have super quick feedback. So you let me know if the quality for you is better tonight. So yeah, so he has some really cool docs here. In fact, I started reading it, even like stuff I'd already implemented, and there was some really interesting and important details that I read about. So stuff I already knew about. This is no surprise here. One thing I did see here, like interesting bits. Like here he talks about how, the 4 mux states for rendering. Well, we use the 3 here. Integrator for vector Y, XY integrator offset, and Z value, the brightness. And then it was this one here, audio hardware. And he says, the only known use of state 3 is the playing of samples, since this is a direct connection of the DAC value to the audio hardware. Then he puts eq, help, and spike. So this is really cool because there are these games, like the spike game, where you'll hear sampled audio, like voices speaking, saying eek, help, or spike, and this is how it's done. So it's a good thing to know, like when I implement audio, that in this mode we just take the DAC values and just play them, just produce that as a signal at whatever sampling rate we're supposed to do it at. What's interesting too is this is what I had also deduced last time, was that the same select lines are used to demultiplex the joystick analog potentiometers. So if you may recall, if you saw me last stream, I had kind of figured out, I was like, oh look, they're using the same bits the mux bits, you know, the bits 1 and 2 with the mux selection mask here, well, they, like, you know, my initial code for using them was here. Like, if the mux is enabled, which meant that, you know, come up here, the bit 0, mux enable, right? It's considered enabled if the value, the bit is set to 0, right? So that's what I'm checking here. I say if test bits mux disable. If it's not, that means it's enabled. And if it's enabled, then I go and I read those 2 bits, the selection mask. And here are the 4 cases we just saw, right? The y-axis integrator, x, y, z for brightness, and then the sound thing that I haven't done yet. Well, looking at the way the BIOS is written for joystick input, I had figured out that actually it looks like those same bits are used when mux is not enabled, right? So, is it here? No. Here, analog input. And basically I check if it's, in this case, if it's not enabled, then we still read those same mux selections and we make choices based on that here, you know, and I think it's inside this function that I have a kind of a, yeah, 0 maps to joy mux 1x. So basically 0 and 1 select the x and y for the first joystick, 1 1 select the x and y for axes for the analog of joystick 2. So that pretty much maps to what he says here. So I was happy to see that, you know, what I had figured out matches up with what he wrote here. So that's cool. And then he says, for more information regarding joystick input, see joyport devices, which we will be doing tonight. Other things I was reading here. Yes. So this is also something that I kind of deduced last time, which was how, if I come back to here, for digital input, I had noticed that the code sets the sound B direction and sound BC1 bits in port B to certain values. Like if the sound B direction is false, but sound BC1 is enabled, is true, so 0, 1, then we are in, then we read data direction A in input mode. And the data direction A is in input mode. Then we do this read joystick, and this was kind of like, you know, feels like a hack, right? I don't quite understand what the relationship is here. Well, this guy totally explains it. He says the above 2 bits are again bundled to 4 different possible states of communication with the PSG chip. Now, the PSG chip is the sound chip. That's the audio chip on the Vectrex. And the audio chip is connected to the joystick ports. And so he talks here about like the 4 values, like if you consider these 2 as kind of like a selection mask again, you have 0 0 0 1 1 0 and 1 1, and he says what each of these modes represent. And like in our case, let's see here, bit 3. So actually it's flipped the other way around, where I have BDIR first and BC1 second. So in my case, I'm looking for 0 1. Here that maps to 1 0, which is this one here, right to PSG, right? This signal indicates that the bus contains register data, which should be latched into the currently addressed register. Okay? So in here he says DA7 to DA0 are in input mode. Okay, so what this is saying is that this is a mode where whatever we put into, let me see here, did I get that right? BC1, yeah, BC1 is on. Mind you, I'm actually reading here. Bit 3, BC1, bit 4, BDIR. I thought that made sense. Bit 3 is BC1 and B4 is that. So I'm checking if this is 0 and this is 1. Yeah, so 1 0. Yeah, I'm not quite sure what the deal is here. Okay, so if it's 0, 0, the PSG is inactive. And if it's 0, 1, which is what I think I'm supposed to be dealing with right now, is read from PSG. Because this is what I would expect, right? This signal causes the contents of the register, which is currently addressed, to appear on the PSG CPU bus. DA7 to DA0 are in output mode. So I think here DA7 to DA0, that's port A, right? And I believe what we're reading here, and that's what I think I'm dealing with here, is these are in output mode, and like the contents of the register, which is currently addressed, which I believe is what is in the data direction. I don't know. See, I'm not sure. I gotta... You know what? I'm sure that they go into more details when we read the joystick stuff. So, anyhow, a bit unsure about this 0110 here. But the point is, like, once we figure this out, we'll understand what those 2 bits are for. So there's one mode that's read, one mode that's write. So, like, in one mode, we can read values from some register that we specified on the sound chip. We're saying, I want to get those values. Alternatively, we have the write mode, which says, I'm going to be writing values to port A, and I want those values to be sent to the currently addressed register on the sound chip. So there's some way that we specify which register on the sound chip, and then we know how to pass input or get output from it. And then finally, there's this other mode called the latch address. This signal indicates that the bus contains a register address which should be latched in the PSG. Oh, so that's interesting. So maybe that's how this is done. Is you first go into this mode to tell it which register you would like to address. You give it time to do that. Then after that you say, okay, now that I've set up the register, I can either read or write. That's probably how it works. And in fact, you know what? I remember when we were looking at the code for the digital input that before it did this 0-1 thing, it did 1-1. It did set both bits on, and then probably it was writing to port A, you know, some register index. So we can take a look at that again later. So communication to any devices connected to joyport is done via PSG. There you go. Like I said, the joysticks are connected to this sound chip. See also joyport devices for more information about accessing PSG chip. Bit 5, comparator input. So this again, we were looking at the comparator last time to figure out analog, and again it's related to joyport devices, so we'll take a look at that. Bit 6, external device. So here it's interesting too, this is fun to read. He says communication with cartridge, bank switching, RAM, EEPROM. So I'm gonna have to implement this stuff at some point because I know that some of the carts make use of bank switching. Some of them enable actual, like, you know, enabling on the cart you'll have some writable memory that you can use, like expansion memory, to expand the amount of RAM because there's so little of it that's available in the Vectrex. So an EEPROM here, I guess. I think that's like we're talking about specialized carts that were made later on, and like probably there's a way to like switch. I think, for example, for multi-carts, I'm guessing that's how they work, through this communication, this external device that's connected to a pin in the cart. So here, this is what we already know there. Bit 7 ramp. The ramp bit controls the activity of the integrators. If ramp is 0, integrators are active. If ramp is 1, integrators are not. Depending on the settings of the VIA registers can be set by accessing bit 7 and port B, or is controlled by timer. So this we pretty much nailed, or seemingly so. All right, so then he goes here into, what is this? All right, port A, register 1, the VIA port A. Simply, so this he says, simply the digital register that serves as input to the digital to analog converter, the DAC. If BC1 and BDIR are configured, the port that sends receives from the data to the PSG. So we know that. Data direction register for port B. So port B can be used as an output register or as an input register. So ORB, output register B, input register. IRB is input register B. The configuration for input and output can be set for each bit of the port. Usually all bits except bit 5 and 6 are configured as output. Bit 5 and 6 are configured as input. Bit 6 is connected to the external line of the cartridge interface of the Vectrex. Because of this, bit 6 can be used to communicate with hardware inside cartridges. Many multi-cards and other hardware use bit 6 for this purpose. See bank switching. So there you go. The tricky thing with Vectrex is if PB6 is configured as input, bit 6 goes automatically high. If set to output, it goes to low automatically. Even if in output mode and a 1 is written to BB6, it only goes high for a short period of time and then switches back to low automatically. Okay, I guess we'll learn more about that when we learn about bank switching and how this works. Register A, the shift register. So this, we implemented the shift register, but you know, what I was showing last time, and I guess I can just run it here. Let's take a look at the emulator again. There's definitely something not quite right with the way we draw text. So like here, and I showed this last time, but basically the text here is slanted rather than straight. It's supposed to be straight. It's supposed to look like this. So you see how like it's all straight? Here it's slanted. And so my suspicions here are something to do with number of cycles or perhaps the way the shift register works. So one of the things that I read here, he says in Vectrex terms, a shift register is one of the most important registers of VIDE since it can control the CB2 or the blank line. The shift modes can be set with register B and are described here. Each time a shift outputs a bit, that bit is placed into the CB2 line. Shifting out a 0 enables blank, light is switched off, and each time a 1 is shifted out, blank is disabled, light is switched on. Okay, we know that. The shift direction is most significant bit first. The bit 7, see this is weird, the bit 7 is rotated back to position 0. Now see, that does not line up with what I figured out. I had read this in a couple of places that bit 7 is rotated back to position 0, but when I had it like that, then we had that kind of like messed up rendering, you know? So that's super strange and surprising. But if we keep reading, other things. He says shifting is done each 2 processor cycles. So I did do that. Shift out at system clock. He says a complete shift cycle takes 18 cycles. So that's odd, right? 18. So, we would expect 16 cycles because there are 8 bits. But he says here, the last shifted value is held for an additional 2 cycles. So that's interesting, right? That means that whatever the last bit is, or let's say we have an 8-bit value, every 2 cycles it shifts out, apparently rotates. But when it gets to having shifted, let's say 8 values out, the last shifted value, we don't, it's almost like we skip a cycle. So we wait 2 more cycles before we shift again. Which means that if the last bit was on and we turn the beam on, that little bit will draw longer than what we would have expected in terms of patterns. So I find that really surprising. And then it says here, if a shift cycle is interrupted, so here he talks about interruption, and apparently let's say you have a shift going and then you interrupt it in the middle of the cycle, VIDE can stall. current shifted out value is held, no further shifting occurs. The time at which a stalling occurs appears to be dependent on the VIA generation. Known values are 14 cycles and 15 cycles. So from what I understand is apparently if it's in the middle of a shift cycle and you write again to the shift register, it won't do anything, or I guess the last thing that it did, like the last thing that got written out, will remain that way for about 14 or 15 cycles before it resets with the new shift value in there. Now, I don't suspect that we need to worry too much about this because I guess games probably don't do that, right? They probably wait long enough for the cycle to finish, maybe. And he says, attention, the 6809 instructions clear also reads from the value before it clears it. Thus, an instruction clear shift reg reads the shift register after 4 cycles and writes the shift register after an additional 2 cycles. So I know that we have clears on the shift register in a couple places in the BIOS. It reads the shift register after 4 cycles and writes the shift register after an additional 2 cycles. Okay. So may be important for timing and for things to look right. And a shift is started by reading and by writing to the shift register. Then he says, why 18 cycles and 9 shifts? 9 shifts, eh? This is because most VIA ships, all Vectrex used ships to my knowledge, have a bug. When shifting using Phi2, mode 110, see below, VIA outputs 9 shift pulses. The last shifted value is repeated. So there you go. So that's something that I didn't do. So there's 2 things here that like are interesting to me. There's this extra, you know, taking the last bit and the last shift and making it happen twice, which we should emulate. And then there's this thing about rotating bit 7 back to bit 0, which never made sense to me because if we do that, then when the beam is on its way back for the font, it ends up writing whatever last pattern was in there on its way back, which is what messed up our font drawing last time. So, yeah. The only thing I can think is the only thing I can think about here is that perhaps what this is saying is that you write the shift register, and upon writing to it, it will perform a full shift cycle that takes 18 cycles, right? That's what he calls here. A complete shift cycle takes 18. And then when it's done, the original value you wrote in there is still in the shift register because it's cycled back through, but then the shift register is no longer being updated at that point. You know, like it's as if it's turned off. That's probably what it is. And so why is that important? Well, it would allow you to read from the shift register to find out, you know, I guess what was the last value you wrote there, which maybe could be useful. So that's probably what this is about. So, you know what? I'm just gonna take some notes so I don't forget what I just said. I'll put it in my to-do. Fixed drawing. Shift register. And I'll say here 18 cycles for a full shift cycle. Last cycle is repeated twice, or last shifted bit is repeated twice. So I gotta do that, and then I'm gonna do so do roll high bit into low bit, but add the concept of shift register enabled, disabled. And once the full shift cycle is complete, disable the shift register. Disable the shift register. So don't use it to control the beam. I mean, I still have questions there, right? Like, I guess what that means is if the last bit is a 1, then the beam will keep writing. But one thing I think I did notice is that for fonts, the last bit is always 0. So then it would effectively turn it, like keep it off if this is correct. So I think that might make sense. This might be useful for programs that read the shift register value to know what was written there before. Okay. And then finally, no, that's good enough. All right. So just some stuff here about auxiliary control registers. He says usually, this is what I programmed, right? Usually shift mode is always set to 110, shift out under controlled system clock. And that's all I support. So if any of these happen, we're gonna get an assert if it's not 110. Okay, here, bit 7. If set on timer start, the output register B bit 7 goes low, ramp active. On timer stop, yeah, it goes high, ramp not active. Okay, we did that. One shot, timer runs till stop, continuous, timer runs till 0, then reloads, latch and starts anew, 0, 1, 0, 0, same as above without or B bit 7. So, you know, I'm aware of all this, but we only support really the one shot mode because that's the one that's actually used. On normal vector draw, bit 7 is usually set. On normal raster draw, bit 7 is often not set. Right. Okay, I like how he calls that. Basically saying for vector drawing, they use the timer, and for raster drawing, like for fonts, they don't use the timer, as we saw. So you may see 18, right, for one shot without ramp, shift under system. So this is what we see when it's doing fonts, and we'll see 98 for when it's doing vectors. So that's cool. Via control register, the control lines of the for Vectrex analog parts, and for now the lines are most interesting. The CA1 line is connected to the second joystick port of the Vectrex, more specific to button 4. For joystick activity, the control line is not used. However, the light pen devices and 3D Imager make use of that control line. Aha! So the light pen, okay, well, don't care too much right now about that, but eventually I might implement light pen functionality and all that. CA2 0 responsible bits. Yeah, did this already. CR2 responsible bits are bits 5 to 7. Yep, we did that. Although blank is usually controlled by the shift, yes. Together in Vectrex terms, assuming bit 0 and 5 interrupt control for CA1 and CV100. Yeah. Sure. The manual appliance of the blank signal with the control register only has any effect if shift is switched to off. Well, there you go. So there is right there we see the concept of the shift register being off. And it's saying that in order to set blank manually, the shift register must be off. So that's something I haven't done. So let me take a note of that. When shift register is on, setting blank manually via CB2, I guess, yeah. The C register. C register is disabled. Shift register must be off for manual setting of blank. Okay, good. This information is gold. Write a 1 to a bit resets the interrupt flag. So that makes sense. Writing 1 to any of these bits will reset. This is the reset flag, right? That's pretty much what I do. Set interrupt flag. Write 1 to a bit reset. That's actually not what we're doing. It's kind of like the other way around, right? What does he mean by it? Let's see here. Bit 0 CA2 interrupt cleared by read write port depending on independent. Like in our case, and I actually realize I haven't done the same call for timer 2 here. Handle setting of all other interrupt flags. This is what I was supposed to do here. So I'm basically setting the timer 1 flag here, which is bit 6. Write 1 to a bit resets the interrupt flag. It sounds like basically I should do the opposite. If 1 was set, if 1 is passed in, then internally we want interrupt flag to be false. Very interesting. So I'll just make a note of that here. That's not what I'm doing. Okay. But I suppose that makes sense, right? If you write to this register, the whole idea would be to reset interrupt flags. 0 means don't do anything, and wherever you put 1s, you're saying for that bit, for that interrupt, I want you to go ahead and reset it. So I guess that kind of makes sense. More sense of what I'm doing here. As opposed to what I had assumed was that you'd write 0s when you explicitly wanted to disable a flag and 1 when you want to explicitly enable, but that would be actually kind of painful for a programmer. They'd have to probably read from it and then, you know, toggle the bits they care about. Seems unlikely to be the right way to do it. And then this is the interrupt enable. If bit 7 is 1, 0 interrupt disabled, 1 means interrupt enabled. And if bit 7 is 0, then 1 means interrupt disabled. Wow. Really? I'm not quite sure I understand this, because what I'm reading here is if you write to this register, then based on the value in bit 7, then the values from bits 0 to 6 depend on whether bit 7 is 1 or 0. But then here, bit 7 says indicates whether any interrupt happened. This is probably just a copy-paste mistake from here, because it looks like bit 7 actually indicates whether to interpret 0 or 1 as interrupt enabled or disabled. So yeah, I'm not sure about that. Timers. Yeah, so this we did. The usual settings, and that's what we handle right now. So timer 1 is used to move the beam across the Vectrex, both for just moving and drawing. Only difference is whether the light beam is switched on or off. For this, timer 1 is configured to the so-called one-shot mode. The timer starts when something is written to the high byte. So you usually see something like clear T1H when timing starts. Yes, we actually figured that out. Using timer 1 in one-shot mode has one neat effect. The 7-bit of via ORB is automatically set to low when the timer starts, and automatically set to high when the timer is finished. So that's the whole point of it. Bit 7 of ORB is the analog equivalent to ramp. Setting PB7 to low means enabling ramp, and setting it to high means disabling. So using timer 1 in combination with its ability to directly control the analog integrators makes it just about perfect to draw vectors for Vectrex. In Vectrex timer 1, low value is usually referred to as the scale of a vector. Yes. Timer 2 is used to track system time and wait for 50 hertz to be reached, and then to do a recalibration. So it's 30,000 cycles. This value can be set to Vectrex RAM, and then there's a colon and nothing. Okay. So yeah, lots of cool stuff in there. Here's some stuff about the PSG chip. And oh, print string. Huh. This is interesting. In the disassembly from Bruce Tomlin, which is the one I've been looking at, there are many garbled comments. Ramp on off switched means like that's exactly what I saw as well, right? So if those of you watching my last few streams watched me read this code for print string and like realized that the comments that said ramp on, ramp off were incorrect, and so I had to correct all of them. T1 shot enabled, disabled, yeah, that too looked incorrect, although I didn't care as much. So he went in and he actually fixed it. So that's cool. Oh, actually he added some really nice, look at this, he actually puts how many cycles each one of these is expected to take. I believe that's what he's doing here. Yeah, one letter is drawn, one row that is, in 18 cycles. 13 cycles overhead. Ramp is thus active for number of letters times 18 plus 13. Now that's really useful, because I can totally validate on my end how many cycles it's taking to write characters. Oh, I like that. Actually, here what I wanted to say was this. Okay, this is super cool. I'm gonna just take a little comment, add a little note about that. Print str exact number of cycles for drawing characters. So we'll definitely check that out at some point. The one thing I wanted to do actually in my debugger is print the number of elapsed cycles for each instruction. I'm not doing it now, but it would be trivial. And then we can literally just step there and see if we're getting these values, right? And that'll answer a lot of questions about whether the reason why we're getting the slanted fonts is because of the cycles not being perfectly accurate from the CPU. If they are being returned accurately from the CPU, then it's got something to do with the way we're consuming those cycles in the VIA chip. Like, for one thing, the fact that the shift register looks like it actually has 2 extra cycles in the way it works may have some impact on this. Maybe. Yeah. Okay, so if we keep going, so now the one that interests us for today is this one, joyport devices. So let's see what he says. How long is this? Oh, not too bad. Just some code at the bottom. This looks really interesting because part 2 is joystick, which is what we want to see. So let's just go over the first part, because I did implement that, but probably am not quite getting it perfectly. Below, I mainly explain how to use buttons to transport data to a device connected to the joy port. If you understand the below things, it will be easy to read such simple things as button states. So for now, I will not explain that. Vectrex has 2 joy ports. Both are wired. I will say button X whenever I refer to pin X. And what I really mean is the device connected to pin X. Port 0 button 4 is wired to the 6809 FIRQ line. Port 1 button 4 is wired to the 6522 CA1 line. Oh, that's super interesting, really. So button 4 is connected to the CPU's IRQ line. So pressing it causes an interrupt. if that interrupt is enabled. Both lines are directly connected to the button outputs. These connections are not going through PSG chip first. Devices, except for paddles, on the joy ports usually only use the 4 buttons to communicate with Vectrex. Light pen, imager, link cables, Vex speech. Although in theory all devices can be plugged into both ports, usually only port 1 is used for these devices, since the Vectrex user is used to having a joystick in port 0. So he is talking about like not the joysticks, but like light pen, the 3D imager, and apparently link cables and Vex speech, I don't even know what these are typically connected to joy port 1, the second port. All programs making use of these devices have to adjust to the ports, and they usually don't do that. Okay. I think he means that you can tell you can program the system to say which port you want to read or not, and I think nobody does that, so they're just always set into default state. The only device known that actually is used in port 0 is the light pen. There is one program, Engine Analyzer, which expects the light pen in port 0. Okay, there are 2 types of communication possible. Direct, unidirectional communication, device to Vectrex. The direct communication can only be used from the device to the Vectrex. This can be done via button 4, which is connected to CA1 or FIRQ. So that's what we saw. Indirect, bidirectional communication is possible using the PSG chip. So that's the one we're mostly interested in right now. Port 0, button 1 to 4, connected to the 4 lower bits of port A of the PSG chip. I'm just thinking about how this is not the same port A that we're talking about in the VIA. We're really talking about a separate chip that has its own register, port A. Port 1, okay, let me just check something. Right, so even though it's not the same port A, it looks like those bits are connected to the one on the VIA chip. Because like when we read the joystick buttons, we are setting, in this case I just did, you know, joystick 1, and I'm setting bits 0, 1, 2, and 3 to these values, ASDF. But these values end up in port A of the VIA chip. So ostensibly we're connected to port A of the PSG chip, meaning the pins just basically route to that. So CPU says, I want to read through this memory mapped register, which is typically this port A that goes to the DAC, but depending on the mode we're in, instead of going to the DAC, it's going to port A of the PSG chip. So this is kind of like not quite correct what I'm doing here, you know? I think writing to port A here, which in my case really represents the DAC, is probably wrong. In this mode, we're reading the PSG's port A, not the VIA's DAC. So this is probably wrong. And then, yeah, interlude PSG. It is worth noting that the port A has two modes. Input mode, port A of PSG can be written to from the outside, a device in the joy ports. Or output mode, port A of PSG can output data to the outside, a device in the joy ports. Okay. The mode of the port is set by bit 6 of register 7 of the PSG. Okay. It seems that internally the PSG has a special storage area for output values. This storage is not affected by the values which are put to the port A lines from the outside. Upon switching from input to output mode, the values from that internal storage are always restored and set to port A. Okay. Okay, so this port A of the PSG that we were talking about here, it has two modes controlled by register 7, bit 6 and register 7 of the PSG, not register 7 of this guy, right? Yeah. And it's saying that when we're in output mode and we write to it, that value gets stored in a separate piece of storage. For output values. Okay, so what it's saying is that when we're in input mode and we write to this port A, it doesn't touch the value that it uses for output mode. So what I'm reading there is some devices that connect into the Vectrex will write values into the storage, and in output mode, those values are what we read when we read this port A. But when we switch into input mode, like we want to write to the PSG, that storage remains intact. Probably not super important for us right now, but I will do this though. PSG sound chip. It has a port A, not the same as VIA. It has a register 7 where bit 6 controls whether port A is in input for output mode. It seems the output values can also be set while PSG is in input mode. Setting output data while in input mode sets the data to that internal storage area. The actual port A will always read FF when read from the outside while in input mode. Okay. In output mode, the opposite does not seem to be true. When PSG is in output mode, it seems data can still be correctly read from the PSG side, meaning reading from the Vectrex side and reading out PSG register. Reg 14 reads the states of the buttons. My first guess would have been to read an FF in output mode, but this is not the case. Okay, we're missing some information here. Now he's talking about something else here. Okay, accessing buttons. As mentioned above, the joy port buttons are directly connected to PSG port A. To read or write to the buttons, the programmer must access port A of PSG. Connected directly to joystick buttons of both joysticks. Bits 0 to 4 for joystick 0, bits 5 to 7 for joystick 1. PSG, on the other hand, is not connected or mapped to any memory location. To access PSG, one has to go through VIA 6522. Now it gets confusing. VIA also has a port A, register 1. The lines of VIA port A are passed through the PSG chip to the DAC. We are ignoring DAC and all that follows at the moment and just acknowledge the fact that PSG chip is connected with its DA 0 to 7 lines. DA stands for data address. You will see why later, to VIA. So he's saying we are ignoring DAC and all that follows at the moment. I wonder if he's saying like we can just ignore it, more like in theory, but that in practice it's not really ignored, so we'll see. So at the end of the day, to read or write values to the PSG, one has to go through VIA port A. Needless to say that VIA port A also can be input or output, which in turn is configured by VIA reg DDRA. Yes. Now PSG has only one 8-bit line, DA0 to DA7. Has only one 8-bit line as input-output for data. But we also have to tell PSG what we want to do, read or write, and from where or where to. Right. For that purpose, there are 2 other PSG pins available. In reality, 3, but we are ignoring BC2 here. So there we go. Those are the 2 that we were talking about before. Those 2 pins taken together can be read as a 2-bit number with following meaning. Inactive, read from PSG, write to PSG, latch address. With configuring these pins in conjunction with the DA lines, we access the PSG and can read or write values. Okay. Simple example. Task. Read value of register 7. We set the following things of PSG. We set the DA to 7. Then we do this. We set the 00, inactive, 11, latch address. This is what I was I was saying I saw last stream. So basically what you do is you kind of like, it's like kind of strobing a bit, right? You say, here's a register I would like to latch onto in the PSG, and you go inactive, latch address inactive, right? And then you set the mode Now I want to be in read mode. So this here, and then these three are enough for it to know, okay, the current register is register 7. The next thing is, are we in read or are we in write mode? DA can now be read with the value of PSG register 7. Comments. First, set the register we are interested in to DA, hence DA. Address we want to read. Oh, that's why it's called a data address register, because it's going to either have data or addresses in it. Set BDIR BC0 to inactive. This is needed. Switching the state of BDIR BC1 cannot be done directly. Switching to a state different 00 must always be done from state 00. So it's like a little state machine. We need to go back to the inactive to reach read or write or latch. And then set BDIR BC to 11. PSG remembers the value in DA7 as the current latched address, meaning the next read or write access will be done with that latched address. Set this, now we got to go back to 0. Okay, so it's really this 7 00 to 11. So we have to go back to 00 because of the state machine, right? So it's like the idle disabled state. From there we can get to latch. It latches. Go back to 00. Then go to read, because now we want to be in read mode from register 7. That's kind of cool, actually. Hardware is cool. And then read the currently latched register to DA, hence D in this case, since now it is filled with data register 7. Okay, so this totally changes the way I'm going to code this. What I'm going to do is I'm actually going to write a class for the PSG, for the sound chip, and I'm going to have this little state machine going to make sure that it does the right thing. B direction and BC1. These two pins are again set, cannot be read, by setting appropriate bits to the VIA. Yes. More specific, both pins are connected to VIA port B. Even still more specific, BDIR is bit 4 of VIA port B, BC1 is bit 3 of VIA port B, okay? Reading world Vectrex example, real world Vectrex example, writing a value to joystick buttons. So value of A is split to 2 nibbles. The lower nibble will end up in port 0, the upper nibble will end up in port 1. With Vectrex, writing to port 0 will usually be discarded. With Vectrex, writings to port 0 will usually be discarded by an ignorant joystick. Okay. So latch register 7 of PSG. So that's what it was saying. Load A7 into A, store it into port A. Then we want to load what he's doing here. He wants to put 99 into port B. So mux disabled, ramp disabled. Okay, that's it. Setting BC1 BDIR to 11. That's the key here. Is the 1 here and the 1 there. Those are the 2 bits that we care about, right? Do that, we go into latch mode. But what about setting it to 00? Didn't he say we have to always go to first to 00, then go to 11? This seems to contradict exactly what he wrote before. Like up here he says, go put 00 then 11, but here he actually writes 11 then 00. So maybe he assumes it's always in 0, 0. So then he says, okay, he kind of goes, we know we're in 0, 0, so go ahead into latch mode and then disable, and go back to disable inactive. So as long as you always leave the state this way, you should be okay, and I guess you can assume it starts in the inactive state. Or maybe the BIOS makes sure to set it into inactive. That's probably the case. Yeah. Okay, so now we know register 7 is latched. We want to write a value of 7F to register 7. So we put the 7F into A. So he says here 7F to via A DAC. 7F is 01111. Disable all noise and tone in PSG. Okay, so this is like writing, making sure to like disable the audio. Enable output on port A of PSG. Port B is irrelevant since it is at 8912. Okay. Um, 7F to the DAC. 7F to the DAC. Really? Yeah, okay. So I mean, as far so it does write it to the DAC, right? Yeah. Okay, so it's not what I was saying. It's not that when we go into this mode, it's not wired anymore to the DAC. It is using the DAC for this. Okay. So I'll kind of undo this. Although maybe in read mode, that is the case. But for write mode, it looks like it does use the DAC value. Because see, like we write to port A, we store a value, and then that value makes its way into the PSG when we go into this mode here. Write to PSG. Now port A of PSG is in output mode and can be written to. Yeah, I can see why it's confusing. Because first we need to use the vias port A to select register 7. Now that we've selected it, we can now write to register 7 of the PSG again through port A, and which sets internally the mode in the PSG, right? Then he says here latch register E of the PSG. Port A, really? Okay, so port A is actually register E. All right. Latch inactive. So now we've said we want to select that register, and then we write A to port. Read value from stack. Output value to via port A. Output value to via port A to port A of PSG. Note, BC1 BDIR equals 00 is used at the end of each command. This is okay if this is followed strictly, since before each setting BC1 BDIR must be 00, which is still honored. Okay, so that answers the question I was saying before, is why did he flip it from what he wrote? He's saying as long as you're consistent and you make sure to leave it in 0, 0, then this will work. Note, the Vectrex BIOS also supports PSG operations. If you only use BIOS functions to access PSG, then all registers of the PSG are shadows at RAM locations. Really? That's kind of cool. Yes, in reverse order. C83F to C84C. C83F. Okay. So basically, in this range of the RAM, C800 to C87, C83. Yeah. So in this first range here, there looks like these 15 bytes are used as a reverse ordered shadow of the PSG registers, but this is manually maintained by the Vectrex BIOS, meaning that if you use those BIOS functions, every time they, let's say, write to one of these registers, it'll write to the related shadow of it here, and every time it reads, I suppose it also puts the value there. So I guess that gives you a way to query what's currently in the PSG without actually having to go through all those hoops, because it's been cached. You can read those values and use them as you would do directly. To poke a value at register 7, you would do... Oh, okay. So, no, it's actually more of a convenience thing, where if you would like to write a specific value to a specific register, you just use one of these 15 bytes, write to it, and then when you call the BIOS routine, it'll read the value that it wants from here, from the shadow RAM, and then do the hoops that it needs to go through to latch the register, write the value, and all that. Or not. No. No, okay, I go back to what I said before. Because you can see here, it says value to set. I want to set B. So sound byte is some function where it'll, in B you put the value you want to write, in A you put the register of the PSG you want to write to. And you go sound byte, and it says write byte to sound chip and to shadow registers. There you go. Alright. Lots of stuff to code up. Part 2, joystick. So let's just read this. Reading value of the joysticks is not as easy as one might think. I agree. Or you just use the available BIOS functions. That makes it quite easy, but that is explained elsewhere. The Vectrex has one of the first machines to have analog joysticks. Below I will try to explain how they are implemented and accessed. Each joystick direction is implemented as a potentiometer. Although altogether there can be 4 such potentiometers, right? Do you remember how the integrators have access to DAC values? The DAC value goes through a multiplexer. The multiplexer has 2 select lines via port B bit 1 to +2. The select values multiplex the one input signal to one of 4 output lines. The output line is chosen by the values of the select lines. Why am I telling you that? Because with the joystick potentiometers, this is the same. Really the same, since the physical electronic part inside the Vectrex is the same. That chip is a multiplexer demultiplexer. The same select lines via port B bits 1 + 2 select which of the 4 potentiometers is taken as input. That's really cool. The demultiplexer sets the voltage of the one selected potentiometer to a circuit which is connected to the DAC and a special other pin. The circuit compares the value of the potentiometer to the analog value received from the DAC. If the contents of the DAC, the analog representation of a digital signed value ranging from -128 to +127, is smaller than the value gotten from the potentiometer, then the above mentioned pin is set to true, otherwise false. You know, if that's true, if I'm reading that right, I think what they mean is this. That comparator bit, that's what it's talking about, right? It's saying that the value we receive from the potentiometer, meaning the analog value, right? We compare that. No, sorry, we compare the contents of the DAC to the sign. And if the DAC value is smaller than the one gotten from the joystick, the analog, then the above mentioned pin is set to true. So this is actually the opposite way. It's if port A sign is less than this. Curious if that works. Wow, my frame rate's not super good. I think that might be because it's my CPU is maxed out right now. Oh, look at that. Holy shit. You know what, let me switch out of debug mode here. Let me see here, because my CPU is definitely running high, and that's because OBS is taking an insane amount of CPU cycles right now. Why is it taking so much? I'm guessing that I'm like low quality right now on the signal might be low quality. Okay, so it's like kind of working. You see, like when I push left on my arrow, we turn left, and I push right, we turn right. It's extremely jittery, which is probably because of my CPU being all wonky right now. I think. And also probably because of the way my rendering works right now. Now we really get to see the problem of the fact that we draw like and clear and draw every 50 hertz completely unrelated to the real way we should be drawing. So I think that's what we're seeing here. Although the movement's a bit strange. Whoa. It's super wonky. Okay, something's off. If I try to go right, I go slow, and if I go left, I go super fast. This looks like some kind of like weird signed error. Yeesh. Okay. But that's interesting, right? Like, basically, what we just read from the guy's doc kind of cleared up what we were doing here. The comparator bit is supposed to compare that value that we write to port A with the analog value that we read from the joystick. So that kind of answers that part. Oh, Alvaro, you saw that? By the way, has the signal cut out yet for you? Has it been better? I think one of the settings that I changed. Let me see here. Does that drop the CPU usage a bit? I'm just messing around a bit in OBS to see if I can reduce my CPU usage. One of the problems is that I don't have a good graphics card, so I don't have hardware encoding. So it's all being done on the CPU right now, which means that it utilizes enough of my CPU that I can't run something else that uses a bunch of CPU, because then everything starts to jitter or like the stream starts to reduce in quality. Okay. The pin, how could it be otherwise, is again part of the VIA. It can be found in port B, bit 5. The bit pin is cleverly named comparator input pin bit, meaning input from the comparator, not input to the comparator. With that information, a digital request in pseudocode can be done like, question, is joystick port B moved to right? The streaming is super smooth, Alvaro says. Oh, good. And you can read, right? Like, if I show code like this, it looks fairly legible to you. Like this, I imagine is quite legible because it's large font, but in code here, I could increase the font size, but I've already gone to 120%. You know, normally I code like this at 100. So disable mux, DAC 0, mux selection 00, enable mux, delay short, disable mux. Wonder why you gotta go through this dance here. Normally, if you disable the mux and write this goes into the X register. Then you select 00 enable, and then that puts 0 into the Y register. Delay short, okay. Disable mux, so this goes back to using the multiplexer for joystick reading. Delay long, load DAC with some positive value, check compare bit. If set, then joystick was moved right. It's cool, right? To get an analog value in principle, the same must be done, but you have to test more. Alvaro said the code looks super sharp. Alright, cool. To get an analog value in principle, the same must be done, but you have to test more. That's so crazy. It's all about testing. Because because you can't actually read the value. You write your compare value and you keep checking the comparator. The line load DAC with some positive value and the checking afterwards has to be done with increasing values till a point is reached where the flag is not set anymore. The last set value, or the first unset value, is the digital representation of the potentiometer of the current joystick axis. This is why it is usually a good idea to only use analog values if it is absolutely necessary, since it is time consuming to do the approximation. Isn't that nuts? It's like, rather than be able to say, read the value of the analog stick, all you can do is say, I'm going to give you a value to compare against, and you tell me if the value that I'm giving you is less than the actual joystick value right now, right? So if you want to get the exact value, and this is what that code that I was reading last stream is doing, is you want to keep increasing that value over time until you get a result. And until the comparator bit changes from false to true. And at that point, you have some power of 2 bits precision value for what that value might be. Real life example of digital joystick request for port 0. Anyway, to be honest, I don't care that it's like that, because that's more like if you're writing a game and you really want to make it based on analog values, you would care about this. In my case, since I'm emulating, I just need to make sure I return the right values and turn the comparator bit on when it's correct. So I think I'm doing that. And I mean, right now I'm not even doing anything that's remotely analog, since I'm just pressing arrow keys, right? So I'm just maximizing the values. There's one thing I wanted to check here. Let's see here. Port A signed. Okay, what I wanted to see was, right now, when we come in here, yeah, I don't think what I'm thinking about is whether or not I'm putting this code in the right place. I feel like this is not where I should be putting it. And rather, I should be doing this when we need to read the value. Like here, when we read port B, for example, right? At this point, I can go and do this here. And similarly, when we read port A, I can do the digital input part. Right. This probably won't compile either. This is a const function, so what we'll want to do here is I don't know. Is this right? Yeah, let's try this. And let's just port A. Let's try it this way. I want to see if it makes any difference. No, makes no difference. There's something definitely funky going on here. See if I'm facing right, I move just a little bit, and if I'm facing left and I just tap, it's like really crazy. It seems like when I'm in the, yeah, you know what, it's got to do something to do with sign, because you see when I'm in the first, say, quadrant, right, where x and y are positive, it moves more as I expect. But as soon as I have some negative value, it doesn't work properly at all. What could that be? Yeah, see, like when I'm facing into the negative y direction, I move down a lot, and if I'm facing into negative x direction, I get both y and x. See, here I have positive y, so I move correctly in y, but in x I move too in the negative, because when x is negative, I move too much in x. If I have both x and y, I move too much in those directions. If I go like this, I have positive x, so I'll move correctly in x, but I'll go too fast in y. Exactly. So definitely there's something here to do with sign. Most likely, what could it be? This has to be like something wrong in one of my CPU instructions, not handling sign correctly in one of the arithmetic operations. That's my guess. So one thing we can do, so I think this, what I did here is fairly accurate. So let's remove this here and let's get this checked in, because we have like basic input working now, right? It's not at all complete, and I definitely want to do the PSG chip and all that. But this is a good step in the right direction. So let me get this committed. Yeah, that was my hack to get it like running decently in debug. This is also a hack. So many hacks. Oh yeah, I did the data direction stuff here. Let's say via via implement or respect data direction A values. When only update integrators if in write mode. It's probably not even correct, but whatever. Gets us closer. Okay, see, like all of this here is not going to remain this way. Like this, the fact that I'm checking, you know, keyboard states and stuff right here, this is all temporary. Eventually, I'm going to want to abstract the notion of what, you know, Vectrex inputs are set and all that, and have that get passed in from the, in the case of SDL, from the SDL layer that I have, right? The SDL engine. But like if we have a different engine, it'll, you know, pass values in whichever way it wants. But for now, as we develop this, this is fine. So I'll say via initial implementation of input or joystick input, ASDF for buttons 4 to 1 and arrow keys for analog. I'll say joystick 0 input. I'll just push it. Okay, so what did I want to check? Yeah, so one thing I wanted to try is something I've done in a previous stream is I have this Vectrex CPU integration, right? I'm just gonna cherry pick this. Let's see. So this is basically a little hack where I took the CPU implementation of the Vectrex emulator and like shoved it into my emulator so I could use that one instead of my own CPU implementation as a basis of comparison. And I'm just interested to see if I use this CPU, what does it look like? Okay, so that's interesting because I still have the slanted font, and that's interesting because actually let me just make sure that it's enabled. No, okay, it's not enabled. Alright, so that makes more sense. Let me go see here. CPU. Right, I gotta set it to 1. I should probably have saved that in my commit. Alright, I need to run cmake again. I need to run CMake again because this change adds a couple files. So okay, so now it should be running with the other one. Aha! Check this out. Letters are straight. So that pretty much proves it. My cycle counting in my CPU is not correct. So that's, now we know what we need to fix for that. Very interesting. See, now everything's straight. No more italics fonts. Okay, cool. So I can totally fix that. So I still got the scaling problem on the ship. Let's see here. Oh, wow. And I'm moving correctly. Still not seeing my shots, but the game has moved forward. So see, my bugs right now are really around the fact that there's probably some invalid arithmetic operation going on in one of my CPU instructions. And the fact that that these guys here, the mines, don't look, or like the asteroids, I guess, don't look correct, is probably related to the shift register timing stuff, or again to the cycles not being done correctly. But I assume that these here are being drawn using the timers, so my guess is probably more about the shift register. Interestingly, the ship is completely solid and correct. Alvaro, are you seeing this? So using the other CPU, I'm actually getting into Mindstorm a bit better. I'm not able to shoot though. But I can teleport and I can move. Very, very interesting. Yeah, so you saw that? So that's not my CPU, right? I'm gonna keep repeating myself. This is a CPU implementation from another emulator. I have never actually really looked at the code. I just took it and it compiles, and like I just looked at the header file for it. It's here. I just looked at this header file and I was like, okay, there's a read and a write function that I need to hook up, a reset and a instruction step functions, and that's very similar to my interface. So now I just hacked that in, and I actually haven't looked much at the CPP file here. So and I kind of want to keep it that way because I don't want to cheat too much. But yeah, once I fix the CPU, the cycles, it will look much better. It'll look like this. So one thing let's say I keep this like this. I'm curious about that shift register thing. So maybe I have about 15 minutes. Let's try hacking in 2 extra cycles in there. And this kind of concept of the shift register being on or off. Do I need to do that? Maybe not. Let's try and do the extra shift out. Okay, I'm just gonna hack something in here. Instead of making this a bool, what I'll do is I'll make this an integer. And I'll say shift cycles left, right? So when we set a value, we'll set this equal to 18. Does that make sense? Yeah, let's do that. And then in here, what we'll do is we'll say if so if this minus minus is greater than 0, I don't like that kind of logic. We'll say if the M shift cycle is left is greater than 0 and it is a even number, we do it, okay, and then after that we say actually 2 ifs. And then if it's greater than 0, we'll bring it down by 1. So here we have 18. We're going to call update shift with 2 cycles immediately, which means that we're going to come in here and we're going to say this is 18, yes, it is divisible by 2, so we will immediately do this. And shift, this becomes 17, and on the 17th one, then it'll come through, it's not even, and it'll go down to 16. And we make it greater than 0 because we don't want to do it on the 0th one, because we're already counting the 18th one. So that should give us 9 shifts, right? 2, 4, 6, 8, 10, 12, 14, 16, 18. Yeah, that's 9 shifts. So let's see if that changes anything. Oh, I have a mismatched brace somewhere. Oh, that's not looking too good. I think my initial thing is not working. So what am I doing wrong here? Check. If it were 16, it should behave as before. But I'm suspecting it won't. No. Okay. Okay. So we just did an update. We have 18, we just passed in 2. So for 2 cycles, we come in here. This is even. This becomes 17. We don't do the next one, right? And then this becomes 16, and we're done. And we still have, so now we have 16, and now we're going to be doing 3 cycles, or I guess 4 when we came in. It was 4. Now we have 3 left. So we're coming in with 1 cycle right now. So this one here should go through. Does nothing. 14 goes through. 13 does nothing. 12 goes through. 4 goes through. 3 does nothing. 2 goes through. 1 does nothing. And then it wrote to shift again. I'm just waiting for when the shift register actually gets a value that's not 0. Oh, here we go. So that's a proper pattern. Looks like if I recall, this is the pattern for V. So blank should be false. So if blank is false, then it should draw. And then we shifted left. So blank is false. I think I know what's happening. I just don't understand why it wasn't happening before. Oh, right. Because we wanted to shift out on the second cycle, not on the first. So I'm setting 18, but I wanted to shift out on 17. So we do it on the odd value. Now if I do it this way, I think I need to wait until it's greater than or equal to 0. No, does that make sense? No, that doesn't make sense. No, this should still work. Let's see. Oh, it's worse. So what I was doing here, setting shift cycle to true. We come in here and then we set this, it becomes false. So then it'll do nothing, and then on the second one it becomes true again. So that is on the second time that we actually set blank. So now what I just did should have done the same thing. So shift value, yeah, it looks like again like a V. Set that to 18. I'm an idiot. That's not how you check for odd values. Okay, there we go. It's much better. So let's see now if it does the right thing. See, one thing that you can kind of notice, right? Like things look a little longer, I think, on the right edge. Let's see. Okay, so it did not fix this problem. So now I'm pretty sure that the problem here is a scaling problem. What I mean by scaling is just like the big ship that comes down, we can see it's all disconnected. I'm pretty sure these guys here have a scale value being set that I'm not respecting correctly. And what I mean by that, boom, is here. Let me go see it. This guy, the XY offset. Let's see if this guy ever gets set to a non-zero value. Let's put a conditional breakpoint for when port A is not equal to 0. So it's not that. I lost my... Really? Oh, I'm pretty sure this here is done with a scaling value being set into the m_xy offset here, but it does not seem so. So maybe that's the bug? I wonder if he has anything to say about that XY offset thing. It's interesting, he has a section on programming in C. That's pretty cool. It would be interesting to write a Vectrex game in C++. Since it uses GCC to compile, it should work. You know what I don't understand here is he's talking about setting the 0 and he's saying he measured in hardware the number of cycles it took when you bring the beam to, let's say, the bottom left corner, minus 127, minus 127, and then he tried different scale values. And here scale means timer values. So interestingly, setting a large timer value made it take longer to get to 0. Does that make sense? It's weird a bit, because usually the timer is more of how long you let the thing integrate for, and it's all about the speeds you set in the integrator. But I guess in 0 it's different, because zeroing means it's not the integrator. So in that case, the scale, what the hell does it have to do with this? This is the one that confuses me. The XY integrator offset seems like it's not being set in our case, although I expected it to. He never talks about the XY integrator offset values. Nope. So we know it's not a CPU cycle thing because the Vectrex CPU implementation gives the same result. So it's got to be something to do with my VIDE implementation. What I don't understand is that what I read is, you know, you use timer 1 as a way to, like, you know, they call it the scale. It's how long you want the beam to draw for. But they also talk about this kind of like global scale, which is this XY offset thing, which can be used to basically, like here, right? Like, this ship here is one piece of code that draws a ship of the smallest size, and then there's this global scale, this offset, that is used to kind of add an offset to, like a, how can I say? It's supposed to add a fixed or a constant yeah, so for the X and Y integration speeds, the speed values we set for those X and Y integrators, you can set this third value, the XY offset, to say, oh, always add this to that, to those values, to make them, you know, bigger or smaller, but in a global way. So that's like a full XY zoom in or zoom out. And I believe that's what we're supposed to see here is this ship. I've thought anyway that that's how this ship was built. And it kind of, you kind of see it, right? Because the lines are all short and separate from each other. So I expect there to be an offset applied here so that as it moves down, this offset is going from large to small for the same sized XY integration offset values, like the same speed values, I mean, for X and Y. But I am not getting values for this. I'm getting brightness values, which I'm not right now using, but I am getting brightness values, but I never get... No, sorry, it's not true. I say I'm never getting. I am getting values here, but they're always 0. Does that make sense? Okay, let me do something here. Color. No. Sutre. Yeah, color. And then we'll set this breakpoint. Okay, here. Actually, let me do that again. But let me load my symbols as I usually do. I'm gonna stop soon. Okay. So we are writing right now to port B. So we have 03 and 02 here. So here we cleared port A. So indeed we wanted to put 0 there. And then store A. So actually we cleared it. Okay, and then, sorry, then we wrote A to B and then B to B. We wrote the value in register A, which is 3, to port B. And then we wrote the value in register B to the same port. But I think this is not actually the interesting bit because we're in the vec0ref enable or check0ref code here. Yeah, to clear the DA register. Anything related to XY offset? Clear the XY offset reg. You see here? I wonder if we'll see it anywhere else. So where are we now? Again in the vec0ref enable. It's always the same place. Okay. So it really looks like we're not getting any right specifically for the XY offset register. Set mux to channel 1. XY offset. Okay. You know what? I think that's my cue. I'm not seeing why this isn't happening. I'm still fairly certain that this is the problem. That basically, you see what I'm doing is I'm adding the offset here. Like what we could try just as a quick hack is like, let's make let's try this. Let's mess around a bit with the offset and see if it actually does do what I think it does. And then we'll stop. Okay, we stop here, put some breakpoint in here, and we'll set G offset to like 50. Okay. It's true that would shift both X and Y. So maybe I'm not really applying it correctly. Oh, you would think it'd be that. Yeah, so basically what I'm thinking about is how effectively for if it works the way I imagine, it would need to work such that it would apply to the velocity here without the sign, and then the sign is applied afterwards. So like if the velocity, like if the strength or the speed for X is minus 50 and the offset is 50, we want it to be minus 100. Does it exist, F sign? No. Am I just imagining it? No, it doesn't exist. Right. Okay, so let's try again, setting this offset to like 50. Yeah, not quite. Getting closer. But now I'm not sure anymore it's a scale. Because these guys don't look much better now. No. See, the scale does affect the way they're rendered, but the error remains. So it's not about that. Okay, I'm gonna stop here. Yeah, and next time, next week, we'll try to figure out why those lines are not drawing correctly, and got a bit of stuff to do for in terms of cleaning up the input code, starting to write this PSG chip for audio for now to handle input, but you know, get things started for that. Yeah, very curious about this MXY offset, and how it's actually supposed to work. It's surprising. But I do think the shift cycle stuff I did here fits seems to fit better the model that we just read about, the 18 cycles and all that. So we could keep this. Oh, and one thing I didn't do here, okay, so I didn't do the part about enabling and disabling, which now that I have this whole concept of shift cycles left, I could know if the shift register is enabled by checking whether shift left cycles is greater than 0. Because once it reaches 0, it's disabled. No, actually, yeah, that's it. I can just do what I used to do here. I don't remember what I called it, but like high bit. Instead of this, I think I'd used read bits. It was a test bit? Yeah. It was test bits, but it was like test bit 01 to get an actual value. Then blank was going to be this is equal to 0. And then what we want to do is we want to take shift and then set it equal to m_shift left shift by 1 ORed with this high bit. So that brings us back to making it more of a rolling register, like the new doc was saying, but okay, so I guess I'm wrong. I guess the last state would have been blank off. Oh yeah, that makes sense. If it's 0, it's blank off, yeah. Oh. Whoa. Okay, check that out. Look at that. Yo, it's totally working. Oh my goodness, okay. So what the hell? I don't even understand it. Oh, you know what it could be? So now I'm thinking, what might be happening is maybe what I was saying. Like, does it read back the shift register value to write it back again? Nope, we're not getting a read on the shift. I don't understand. Okay. So the last bit of the shift register is expected to keep, like the last state for drawing the ship and these guys is expected to remain. So like if the last bit is on, sorry, or off, then blank would remain. So confusing. It's blank if it's 0. Right. So yeah, 1 means draw, 0 means don't draw. So the last bit of those shift registers must be 1, so it expects to keep drawing until it decides to draw the next line. Yes. Ah, that's it. Okay, right. Okay, this has to do with okay, so what this has to do is with the interplay between the timer and the shift register. You write, let's say all I guess all 1s to the shift register. And then you say I want to draw for this much time, which it does. No, I don't understand. How does this fix it? Because what I don't get about this is that we're still running it for the same, we're just doing one cycle through this code. The top bit is, oh yeah. Let me think for a sec. Okay. There are 8 bits in the shift register. right? Now, what I implemented was that it will actually go for, instead of doing, every 2 cycles, it'll output this, it'll use this here to turn on or off the beam. So if it's 1, it'll turn it on, right? Turn it on, turn it on. So keep it on, keep it on. But then we read that actually there's 2 more cycles. So 1 more bit that gets shifted, right? But the thing is, if I don't roll, right, this basically becomes 1 1 1 1 1 1 1 0. So we took off this top one and we're drawing. And then over time, right, if we're not rolling back, we're gonna get 0 0 0 0 0 0 0 when we've done the last top bit. So let's say we're here, this becomes 0, and then the next cycle we end up putting 0. So we turn off the beam for the rest of the time. Whereas for the next 2 cycles, right? Whereas if we roll, right, this basically always remains 1 1 1 1, and so that the last 2 cycles that we CPU cycles, or the last shift out that we do, the 18th cycle, let's say, we get a 1 again because we're rolling. So that's like the bug. The bug is that we wrote 8 bits, but we actually shift out 9. The last bit that gets shifted out, the 9th one, is actually the first one. So that's why it's important to roll it. It's either that, or we're supposed to... What did he write again? It's either that, or we're supposed to shift out the first one twice. But no, it is more like what that... He wrote that it rolls, right? So... The last shifted value is held for an additional 2 cycles. Oh, see, that's not exactly then what I wrote. He's saying really it's a last shifted value. But then he does write up here, the shift direction is most significant bit first. The bit 7 is rotated back to position 0. Okay. It's a bit of both. We do shift it back in, okay? That's in case you want to read it. That's like the correct way to do it. Why it's working for us partially, but not fully, like it's not working for text, is because I haven't done this, where the last value is held for an additional 2 cycles. That's what I really need to do. So because for fonts, it's typically, you'll see something like this, right? All the fonts will have some values, let's say XXXX, XXX, and then 0. They're always 0 at the end, right? Because the idea is that it does this, the shift register, and then this here will be the last state, and then the last state again. So it'll, put 2 zeros. But for line drawing, it'll typically be like XXXX, XXX1, right? So then the last state is 1, and then that gets output again. And the reason why rolling was working for us in the case of line drawing is because the first one became the last one, but it wasn't working for font because the last 0 was actually whatever the first value was, which if it was a 1, like for many of our fonts, ends up doing the wrong thing. So I still think that the rolling is not that important, but we can do it just to be correct. But more importantly, we need to make sure that the last 2 cycles are outputting the same value that it output previously, which is to say, on the last 2 cycles, we should be shifting out. What should we be shifting out? The top bit, probably without performing the shift itself. So something like if F shift cycles is is greater than 2. So basically for the last, oh sorry, this is for odd, right? Greater than 1. We always shift, or else we always roll, shift and roll. I'll just say roll. Well, we always roll except on the last, let's say 17th of 18 cycle. Let's just say 17th cycle. Okay, let's see if that works. And it doesn't. Why? Right, this is not correct. I think this might be it, but I don't really like the way it looks. Let's see. Okay, so that's better. Font looks correct. And then hopefully the ship and everything will look correct as well. Yep. Okay. So this works. I'm not a huge fan of the way this code looks though. It's really hacky. But basically what we're saying is because actually when we get to cycle 3, when we have 3 cycles left, that basically means we're on the 8th bit. And it's at that point that we don't want to shift because we want to keep it the way it is. So that on the next one, the 9th bit, we take the same top bit as the 8th bit. The 8th one. The other way to do this is to remember. But that's kind of sucky as well, right? So I kind of feel like just not shifting. But then the question is, does that leave us in the correct state? Because technically we should have shifted out and then we should have kept, yeah, we should have done the shift. That's why this is not a great solution. So another way to do this, that probably is cleaner, is to go like, we always shift, although we actually don't want to shift when it's like this, but then the bit we read depends on whether or not we're doing the last cycle if it's the last cycle, this is way more explicit. And the tricky part here, and I don't know if I got this right, but let's see. Okay, so far so good. So much for stopping early. But you know, once you're having fun, it's hard to stop, right? Yeah, it totally works. Okay, and I'm much happier with this code, and I think it's way more explicit about what we're trying to do. Basically, what I'm saying here is, if it's the last cycle, meaning we have, you know, 1, the value here is 1, we want to reuse the last bit we output last time, right? Which would now be in bit 0. And we don't want to shift anymore. I think that's correct. I'm not sure about that. He doesn't actually talk about it. Because it says here the last shifted value is held for an additional 2 cycles, right? So I don't know if it means we're supposed to shift the last one or not. But let's say we're not going to. And then the usual case is we shift out of the top bit. Here, let's invert. No, okay, let's do it like this. I'm just gonna put a little comment here. For the last 9th shift cycle, we output the same bit that was output for the 8th, which is now in bit position 0. We also don't shift, which I'm not sure is correct. I'll say we also don't shift. Is that correct? Yeah. Okay, so there we go. This is good. Happier with that now. So let's take these two and submit that, and then I'll really stop. Okay, fix, I'm gonna say via fix drawing of, no, how do I say this? Implement shift register no, fix shift register implementation so that it correctly outputs, so that it shifts for 18 cycles and outputs outputs last 16th bit last shifted out bit twice. This fixes ship and asteroid. I think they're actually mines. This fixes rendering of large ship and mines in Mindstorm. So Alvaro, you asked, why does the text have precision errors? You mean like, why did I have the shifting, the kind of italics when it's my CPU? Almost certainly because I'm not returning the correct number of cycles for certain instructions on the CPU. When I use the other CPU implementation, it works, but when I use mine, it doesn't. So I'm going to be looking at that, and I also have to figure out which of my arithmetic operations on the CPU isn't doing the right thing vis-a-vis sign, because when the ship is pointing in negative axes, it totally goes wonky. So there's for sure probably one of the adds or subtract. I think it's probably add with carry or something that's not working. That's my guess. Okay, so that's it. I'm gonna call it quits. So thanks guys for watching, and I should be back next week on Monday. So yeah, hope to see you next time.